Hello physics students, Mr. Dillick here, and this is the video notes for number 16 and number 17. This is going to be about forces and drawing free body diagrams of forces. So pretty much this is a new type of physics that we're doing here in our second unit. This is the start of our second unit, and it's different than what we were doing in the first unit. In the first unit we were studying how things move. We were doing a descriptive type of physics called kinematics. Here we're starting into a branch of physics that's more explanative rather than descriptive. This is a branch of physics called dynamics, and the purpose of dynamics is to explain why things are moving or why they're not moving, not so much to try and describe how fast they're moving or how far they're moving or how long they've been moving. So it's more of a why brand of physics than a how brand of physics. And so that means we're going to be talking about forces, momentum. We're going to be talking about Newton's laws of motion. We're even going to be talking about some circular type of motion called torque. So we've got a lot here that we're going to be talking about. So this is just to get us kicked off here. And so what we want to talk about here is we want to be able to describe why things are moving or why things aren't moving. And so that means we're going to start with the most basic thing, and that's forces. Now a force, there's probably a more technical version of the definition for a force, but as far as I'm concerned, what I really want you to know is that a force can be either a push or a pull. Either one of them will cause the same thing, something to potentially move, and it's going to be a force in some direction. And so these are vectors. They have a magnitude, the oomph, how much you push or how much you pull, and they have a direction. You could pull up, down, left, right, forward, back, or anywhere in between. So they can be one-dimensional forces, they can be two-dimensional forces, or even three-dimensional forces. Forces are measured, their standard unit of force is the Newton. And so when we look and we see that forces are measured in newtons, there's a couple things that I want to make sure to mention here. One is that a newton is the amount of force that it takes to accelerate a 1 kilogram mass. A newton is the force that it takes to accelerate a 1 kilogram mass so that it gets faster by 1 meter per second every second. That's an acceleration. And so the definition of a newton is 1 newton is 1 kilogram meter per second squared. So that's a physical thing to really think about. It's how much force you would need to apply to make something not only move, but get faster when it moves, to accelerate. We've been saying all along that forces go with accelerations, and so here you can see that. Now, quick little side note, where do we get the definition of a 1 kilogram mass? Well, that actually, there's a cute little video that I'm going to show you in class. You can look it up on YouTube. It's called The World's Roundest Object, and it describes how our definition of mass is based on a standard mass that's kept in a vault in Paris, and then that's the 1 kilogram mass. But we're looking to change that definition to be a little bit more like Avogadro's number, based on how many atoms there are rather than how massive something is. Anyway, if the definition of 1 kilogram of mass changes, then the definition of a newton will change, because you can see that a newton is a derived unit, and it's definitely derived based on the amount of mass that is being accelerated. Okay, so anyway, key things here. Forces cause accelerations. This is really important that you understand that. So those two ideas are inseparable. All right, so the newton is the standard unit of force. What are some other units that you can use that are not standard? Well, the pound. And the pound is going to be about basically 1 pound is roughly 4 newtons. And also the dyne. The dyne is a metric unit, but it's a smaller unit. Instead of kilograms and meters per second squared, it's grams and centimeters per second squared. So we're talking about much smaller motion. All right. So forces basically fall into two categories. Contact forces are things that you have to touch in order for the force to act between them. Friction is a really good example. If you rub your hands together, you can tell that there's friction, and so those have to be touching. Other forces are what we call field forces. They don't require that objects touch. A good example of this would be gravity. You can be affected by gravity if you were floating in deep space. you're not really touching anything, the force of gravity could still act on you. So here's a list of some pretty important forces. You would want to memorize these. The contact forces are friction. Tension is found in the string. Centripetal force goes with circular motion. The normal force will come to later, but basically it's a force that says that if you touch something, that thing touches you back, and that force that it touches you back with is called the normal force. Elastic force, which goes with springs. And then if you don't know what else to call the force, called an applied force. All right. And then the field forces, gravity, electromagnetism, and the nuclear forces don't require that you touch anything for you to be affected by those forces. You can get near a magnet with something metal, and the magnet will act on it. You can get near the earth, and gravity will pull on you. And you can get near something radioactive and be in its radioactive field. Notice that the four fundamental forces that hold the universe together, these are the ones that we say, these four act everywhere in the universe. We know that there's always at least four forces acting on everything, never less than these four. Gravity, electromagnetism, the strong and weak nuclear force. The strong nuclear force is really the force that holds atoms together, and the weak nuclear force is what we call radioactivity. Those really occur at the subatomic level, so we don't experience those on a daily basis. On a major level, like we experience gravity. And electromagnetism, same thing. It's kind of something that doesn't come up a lot in our lives in terms of electromagnetic forces acting directly on us, but we are held together by electromagnetic forces, and everything we touch has an electromagnetic force as well, so it affects everything. Please note that these are all field forces. Okay. So moving on to packet number 17 now. We like to analyze forces on different objects. Objects are often called bodies, and so we make what a special type of diagram called a free body diagram. And that's basically a picture we're going to draw where we're going to free an object of all the distracting features of it and just focus on the forces that are acting on it. When we do this, there's specific rules that we follow. We're going to draw all objects as boxes. We're going to put a dot in the middle for the center of gravity. We're going to draw arrows like any other vector. The arrows represent the forces, except we're going to draw them tail to tail coming from the center of gravity, a point in the middle of the object, rather than head to tail like we've done so much with other vectors. And the length and the direction that we draw them are important. So you want to make sure that you draw the arrows relatively long if the magnitude of the force is great, and shorter if it's not. So here's a few examples. I'm going to draw them on my board. Okay, so first I want to talk about objects that are on surfaces. When you draw a free body diagram, you can see that the first thing I did was I drew the object as a box. No matter what this object is, it could be an umbrella or it could be an elephant, it could be anything. We're going to draw it as a box. And you can see that the box is on, I put a line underneath it, and that represents that the object is on a surface. Here you can see over here, this is my eraser, my magnetic eraser stuck to the board. Here you can see the surface is to the right. And if I was drawing something that was maybe hanging from the ceiling, I would put a line above it to represent that the surface was above it. So make sure you include a line if the object's on surface. And then we're going to draw arrows coming from the center. And so you can see here's an example of an arrow that's coming from the center. This one is Fg, that's the force of gravity. This one is Ff, that's the force of friction. This one is Fa, that's the applied force, which is generally what we call a force when we don't know what else to call it. And then this one is Fn, and that's the normal force. It's the force that touches back whenever something touches a surface. So you can see this, because this object is touching a surface below it, then that means that the normal force is acting up because the object is touching a surface that's below it. And here you can see the normal force is to the left because it's the force that touches back when something touches the wall. This Fm is the force of magnetism. And then you can see that gravity is acting down. It's always acting down, and it's always the first force you're going to draw. And then there may have friction acting to oppose the motion of an object. So here you can see this object we're saying is moving. A squiggly line means that the object is moving with a V for velocity. This one doesn't have that, so this object is not moving. Okay, so that's how you do objects on surfaces. What about objects that are falling? Okay, well here you can see 3 different free body diagrams for objects that are considered to be falling. I'm doing little air quotes with my fingers. In the first one, we can see that this object is falling straight down. That's why you can see that it's falling. And when things are in free fall, they would be experiencing no air resistance. And so the only thing they experience is gravity. And so then you can see the only force is gravity. This one is also free falling because the only the force it's experiencing is gravity, but this one is moving up in free fall. So it's on its way up to its apex, and this one is obviously falling. Projectiles technically are only affected by gravity as well, and here you can see the only difference in the projectile is that it has some motion that's not going to be downward. So you can see its velocity is saying that this thing is moving up and to the right. So this is a non-horizontally launched projectile, perhaps. What you see that they all have in common is they only have one force acting on them, and that's the force of gravity. And this one is experiencing a lot of gravity, and this one's experiencing less gravity, and this is experiencing even less gravity because the length of those arrows matter. If I was going to draw an object that was moving, or excuse me, if I was going to draw an object that was falling but was experiencing air resistance, it might look something like this. I might say, okay, well, I've got an object, and there's its center of gravity, and it's experiencing the force of gravity acting on it. And then if it was experiencing some air resistance, if I knew that it was moving downward, I might put air resistance acting up. And air resistance is a type of friction. So that's how you might draw a free body diagram for something that is experiencing air resistance, and this would be not in free fall. Okay, let's try another one. What about objects that are on inclines? These are the trickiest of all. And I should say, the ones on surfaces are the most common, and they're not particularly hard or not particularly easy. They're kind of in between, but they're the most common. These are definitely the easiest, objects that are falling, and these are definitely the hardest. So what about objects on inclines? All right, well, let's take a look. Okay, so when you put an object on an incline, we draw the ramp that it's on, and an incline could be considered uphill or downhill. So technically, these are both inclines and declines. They're just basically the same ramp looked at from 2 different points of views, although I put 2 different objects here. And what I want you to see is that when you put something on a ramp, the normal force is always perpendicular to the surface. And so the definition of the normal is an imaginary line that is perpendicular to the surface. So I kind of put a normal in there. You can see I put a normal in here as well. And so it's an imaginary line perpendicular to the surface, so the normal force, doesn't matter, you can draw this either way. The normal is always going to be perpendicular to the surface. And on this particular one, I put gravity going down, tension, so there's a string or something pulling this block up, and friction going down. And this one is not moving. So this one is at rest on a surface, but this one is moving, and you can tell because of the squiggly line, and it has less forces acting on it. It has the normal force opposing, or from when the block touches, the object touches the ramp touches back, and it has gravity. Okay, one more. What about objects experiencing forces in more than one dimension? What's that look like? Okay, these look like they're really hard, but they're actually not. Pretty much what we're saying is that there are 4 forces acting on this object. 3 of them are one-dimensional. Gravity is straight down. It only goes down. That's the only dimension it has. Normal force is straight up. That's the only dimension it has. Friction is just to the left. That's the only dimension it has. But this applied force, it is moving up and to the right. And so whenever you have a 2-dimensional force, you need to bow tie it. You need to break it into resolve it into its one-dimensional components. And then from here, we could figure out other things. For instance, and I kind of forgot this, what if it's moving in this direction, right? What if it's moving to the right? Then we could say, well, you're pulling up a little bit, but it's moving to the right. So are these forces balanced or not balanced? That would be the key question. And so that's really what I want to end with here is, why do I care about making free body diagrams? What's so special about them? Why do I need them? The main thing is because you want to be able to look at the forces acting on an object and decide if there is what we call a net force. Are they balanced or are they unbalanced? In that tug of war, are there forces winning the tug of war? And if so, by how much and in what direction? Okay, see you next time.